Hello, this is Ellen Gunlack, and I am hosting the JSE Cause webinar for Michelle Everson, who was unable to be with us today. And I would like to welcome all of you to this webinar and tell you a little bit about how the webinars work. First of all of you are muted, and you will remain muted the whole time, but we definitely want your interactions in this webinar. So if you think of good questions you'd like to ask Rob and Michael, please type your questions into the question box, and then at the end of the webinar, I'll be happy to ask those questions to our speakers. Now, Rob and Michael will be speaking about assistive technologies for second-year statistics students who are blind, and we look forward to their presentation. Rob and Michael, go ahead.
Well, thank you very much for the introduction, and good afternoon, everyone. I'm Rob Erhardt. I'm an assistant professor of statistics at Wake Forest University, and I'm joined by...
Yeah, this is Michael Shuman. I'm the interim director of our Learning Assistance Center and Disability Services here at Wake Forest.
And today we want to share with you our experiences teaching a second course in statistical modeling to a student who is blind. And I'll start with a little bit of introductory material on Wake Forest and this particular student in the class, and then Michael is going to share a little bit of introductory material on some of the background of learning assistance. So Wake Forest is a private university of about 4,800 students, and we have a second course in statistics, so the prerequisite is any first course, and in the second course we cover simple and multiple regression, model diagnostics, selection, visualization, and we end with elementary logistic regression. And this course is solidly part of the Stat2 movement. In fact, we used a book titled Stat2. And a few years ago, we had a student enroll in this course who is blind, and she had taken AP statistics at her high school, and she had done quite well, so she was placed into this class. But this class was the first sort of STEM course she would take at Wake Forest University. And what we discovered was a lot of the accommodations that work in an introductory statistics class, or perhaps a math class, were not as appropriate in a second course in statistics. And this is because the mathematics, the computing, and the visualization of the data are sort of more central to the course. They're at a higher level, and there are inherently more challenges. So what we want to do is share a solution to this problem. It's just a complete story of what we did. We don't know if it was the best solution, and we don't claim that it's the only solution. But we're going to show you some of the technologies that are available to students to help overcome these challenges. We'll talk about how we use screen readers, LaTeX, the BrailleR package in R, a Braille embosser, and so forth. And before we do, I just would like Michael to say a few words about the legal and moral background of learning assistance in higher education.
Thanks. Yes, this is Michael, and for those of you who have worked with or ever coordinated accommodations for students with disabilities in your classroom, you may already be familiar with the process of coordinating those accommodations and a little bit behind why we have to do it. So first of all, it's certainly the right thing to do. We want to make sure that the courses that we teach and the information that we provide is accessible to all learners. But there certainly is a legal obligation for colleges and universities. And I wanted to briefly touch on the two pieces of legislation that help inform those decisions. The Americans with Disabilities Act of 1990, also known as the ADA, which was amended in 2008, the Disabilities Act Amendment Act, and Section 504 of the Rehabilitation Act of 1973 are these two pieces of national civil rights legislation intended to prevent the discrimination of individuals based on their disability. Now, at the post-secondary educational level, colleges and universities are obligated to provide what we call reasonable accommodations that allow students with disabilities the opportunity to participate in all of the college or university services and programs, which would include classroom settings, classroom readings, science labs. Now, without guidelines or policies provided by the ADA or by Section 504 that ensure equal access to these educational programs, these students with disabilities would face barriers. They wouldn't have equal access to the post-secondary institution, and they would be prohibited from participating fully in college and university life. Now, as I mentioned earlier, most colleges and universities have a disability support services office on the campus to help coordinate these accommodations and coordinate these services for students with disabilities. So at Wake Forest, our DSS office is part of a larger Learning Assistance Center and Disability Services. So we're not only coordinating services for students with disabilities, we also have a general academic support office providing tutors, academic coaching for any student interested in improving their academic performance. Our staff members, like myself, work closely with university faculty and with students to make sure that we can facilitate the implementation of these accommodations on campus and in classrooms. And the next few slides you're going to see are going to be specific to this one course that Rob is teaching. Actually has taught several times, but.
That's right. So the course here, as I mentioned, it's Stat 2, and here's the textbook. It's called Stat 2, Building Models for a World of Data, and it's a very well-known list of authors in the Stat Ed community. And I went to the website last night, and I gather these authors went back to Sedona, Arizona, and took their photograph in front of the mountain, which is on the cover of their Stat 2 textbook. And the central message of a second course in statistics is to shift students from being consumers of statistics information into being producers. So whereas Stat 1 might emphasize sources of variability and how to interpret data, Stat 2 really gets into how would you produce statistical claims for a full data set yourself. So there's an inherent independence built into the course, independence in that the student should be totally independent throughout the full data analysis. And I found it useful to think about 3 sets of skills that are essential: mathematical writing, computer code, and graphical displays. And for each set of skills, we need the student not only to be able to interpret output, but to produce it themselves. And so accommodating a student who is blind necessarily means filling in these 6 checked boxes on this table. So I want to start by going through a very quick example from the textbook, just to give you an idea of the sorts of problems that we work with. And as I'm going through, I would encourage you to think about, well, how would you make that accessible to a student who's blind? So the data set that I'm going to focus on comes from the High Peaks Mountains in the Adirondacks of upstate New York. So these were the 46 mountains originally believed to be over 4,000 feet tall, although they sort of goofed. They included some that they shouldn't have, and they missed one that they should have. But nevertheless, 46 is locked in everyone's mind. And so 2 variables in the data set are the time, how long it takes to hike from the trailhead to the summit and back, and also the length, how many miles it is from the trailhead to the summit and back. And we might be interested in modeling the relationship between these 2 variables with the simple linear model shown at the bottom of the screen. So we're seeing some Greek letters. We're seeing the errors are said to be normally distributed with a mean 0 and a standard deviation. So that's some basic mathematical writing. To fit this model, we would need to use some sort of computer software, and we use R in our class. So the top 5 rows are the commands that the student would type into R directly. They're loading the data, they're fitting the linear model, and they're asking for the summary. And then the bottom 2/3 of this slide show the standard linear model output from the R program. And students learn to pick off the relevant pieces. So right here, for example, we have the estimates for beta 0 and beta 1, along with information on the t-tests and their significance. Here's the residual standard error down here at 1.449, and so forth. So students learn to pick off the relevant bits of information. They also learn that they need to make sure it was a good model to fit. So on the left, we would look at a scatter plot of these 2 variables, and we would want to see that the scatter is roughly linear and aligned with the correct model. On the right, we might want to look at the residual plot to verify assumptions of constant variance or linearity within the data. We would want to check the normality of errors assumption, and one way of doing that is with a quantile-quantile plot. So that's where we show the sample residual quantiles versus what we would expect under the assumption of true normality. And if those points follow that straight line, the assumption is satisfied. And we might also be interested in looking at a histogram of residuals, and it will become clearer why a histogram is useful, particularly to a student who is blind. So in that short example, you've just seen all 6 check marks here. We needed to produce and interpret mathematical writing, computer coding, and images. And so for the remainder of the talk, we're going to share some examples of how a student who is blind can accomplish each of these 6 tasks. So the first piece of technology that's incredibly useful is screen reading technology. So a screen reader will simply read in a somewhat robotic voice anything displayed as text on a laptop or a computer. And so if you can provide, say, the textbook or notes in digital format, a screen reader will dictate it, and a student who is blind can simply listen. So I wanted to give you an example of this, and these are the lyrics from Bob Dylan's Don't Think Twice. So I'm going to play what the screen reader is reading it, and I hope the sound comes out quite well.
Well, it ain't no use to sit and wonder why, babe, even you don't know by now, and it ain't no use to sit and wonder why, babe, it'll never do somehow when your rooster crows at the break of dawn. Look out your window and I'll be gone. You're the reason I'm traveling on, but don't think twice, it's all right.
So as you might imagine, that works incredibly well for ordinary text, and so providing accommodations in, say, a history or a literature class could be a bit more straightforward than statistics. In statistics, though, you're going to have to write a lot of mathematics, and writing mathematics poses a slightly greater challenge. A standard way of writing within the blind community would be to use Braille, and so grade 2 standard Braille has 6 dots. So they're arranged in columns. I'm showing them here, 1, 2, 3, 4, 5, 6. So 3 on the left and 3 on the right. And at each of these locations, there will either be an elevated dimple or it will be flat, and the student can simply run her fingers over and feel the letters. So if you're good at combinatorics, you might see that there are only 63 unique characters that can be produced in grade 2 standard Braille. So that covers the English letters and the digits 0 through 9 and some basic punctuation, but it's nowhere near enough to cover the symbols in mathematics. So just think of differential calculus and linear algebra and Greek letters and superscripts and subscripts and so forth. It's not enough. So one extension is so-called 8-bit Braille, which adds dots 7 and 8 beneath, and that gives you a total of 255 characters. And the crucial value here is 8-bit Braille covers all of the ASCII symbols. So in addition to the letters and numbers, you get the braces, brackets, ampersands, dollar sign, and so forth. And if any of you in the audience are familiar with the LaTeX typesetting language, you probably know that LaTeX is a way of encoding all mathematical information into ASCII symbols only. And so through LaTeX, you can write all mathematics in ASCII, and then through 8-bit Braille, you can read all ASCII characters. And so in principle, a student who's blind has full access to the information in a mathematical equation. And sighted users often type in LaTeX because they want the computer to then compile that code and display mathematics in the visually familiar format. So in this situation, you can think of the student effectively compiling LaTeX source code in her head. If you're not familiar with LaTeX, I've shown 2 examples of it here on this slide. The top 2 rows show 2 equations from the Stat 2 class, the first one being the same linear model as before. And the second equation is the equation for Mallow's CP. This is a quantity that you compute when you're trying to decide amongst many models which one strikes the best balance between explanation and simplicity. So visually, these look familiar to us, but what I actually typed and then compiled was LaTeX source code, which is shown in these 2 lines below. So you can see the use of backslashes and underscores helps you write Greek letters and mathematical symbols. And the equation for Mallow's CP, you see you designate a fraction and you place the numerator and the denominator and braces and so forth. But the point is all of the information shown up here has been encoded in ASCII symbols shown down here. Now what I want to do is I want to play for you 3 audio files in a row, and it's going to be the screen reader JAWS reciting the equation for Mallow's CP. This is what a student who's blind would listen to. So the first speed is going to be quite fast. This is a speed somewhat representative of the speed the student in our class used after she got quite familiar with screen readers. So that one was probably quite fast and a bit difficult to follow. The next is the middle speed, the central speed that the JAWS software uses. And again, it's going to be reciting the equation for Mallow's CP.
C underline P equals backslash frac left brace SSE underline M right brace left brace SSE underline K slash left paren N dash K dash 1 right paren right brace plus 2 left paren M plus 1 right paren dash N.
And then finally, I want to play it at a very slow speed to ensure that everybody is able to follow this screen reader and how it's used.
C underline P equals /frac left brace SSE underline M right brace left brace SSE underline K / left paren N dash K dash 1 right paren right brace plus 2 left paren M plus 1 right paren dash N.
And so you can imagine, as you become more familiar with the use of screen readers, the efficiency increases and you're able to increase the speed. The other way that the student can read and write mathematics in LaTeX is with a Braille note. This is shown here by the company Humanware. So a Braille note is about the size of a laptop keyboard. And if you'll notice across the top, there's 4 buttons for the 4 fingers on the right hand and 4 buttons for the fingers on the left hand. These are the 8 dots on Braille. So the 4 on the right hand is the right column, and the 4 on the left hand would be the left column. So you can type in Braille by pressing the buttons, and you'll see the space bar in the center. You can also read in Braille by uploading a text file through a USB drive, and you'll notice at the bottom of the screen there's an 8-bit refreshable Braille display. And so digitally, these pins are going to raise and lower as the cursor is scanning across the text file, showing ASCII code or ordinary text. And that way the student can read both mathematics and ordinary text. So the next row on that original table was the use of software. There's really no way of fitting these models without some kind of software, and we use R in our class. And the central difficulty with R is it does not work well with screen readers because of the number of nested windows. If you've ever used R, there's the outermost window, but inside there's a console window, a script, the plot window. If you use RStudio, that splits into 4 windows. And of course, a sighted user can use the mouse to click around, but a blind user could not do that. So the workaround is to open R in the terminal window. This is the old classical C prompt, which is behind the scenes of Windows. By opening it in the terminal window, you force R to run entirely within a single window, and so you can type and get output, and the screen reader will recite everything shown on the left. There's an R package written by Jonathan Godfrey of Massey University, which is located in New Zealand. And Jonathan is himself blind. He wrote the R package BrailleR, and it contains a number of excellent features that extends the accessibility of R for blind users. The 2 that we made heaviest use of is the text start command. The text start command keeps a log file of everything the user types and everything that R outputs. So it saves it in a running text file, and this allows the user to go back and rehear things. You know, what model did I fit before? What was the output again? I think I missed what the parameter estimate was, and I need to hear it a second time. So you can move back and forth between these windows. The other command, which is incredibly useful in the BrailleR package, is a function called VI. This is a wrapper function. You run R functions within VI. And what VI essentially does is if there is a straightforward way of conveying all of the information in text that would be accessible to a blind user, the function VI will produce that. So I'm showing again the residual plot from earlier. These were the residuals from fitting the time versus the length of hikes. And sighted users might make this figure because they're interested in assessing normality or checking if the residuals are skewed. What's shown on the left here is the output for making a histogram within the VI command. So the VI command is simply dictating all of the relevant information from a histogram. It tells you what's on the axis. It tells you how many bins you have. There are 8 at equal width, beginning at -3 and ending at 5. And then it just goes down and gives you the counts of the bins. So that is conveying all information of a histogram in a very accessible format. And finally, for images that cannot be described in an obvious way, we made use of a Braille embosser. So a Braille embosser is a printer, but rather than printing with ink, it punches dimples into very thick cardstock quality paper. and it can be used to print Braille text, but if you make an image large enough and pixelate it, it can also be used to print images. So what I'm showing here is the same scatter plot from the beginning of the talk. This is the time on the vertical axis against the length on the horizontal axis. It's very easy to pixelate an image using the software that comes with the Braille embosser. And then what I did is I typed the labels, that says L-E-N-G-T-H, parenthesis, M-I-L-E-S, close parenthesis. You type in English, but Braille displays, and then you can move the labels around where you want. And I've labeled every other tick mark that says 5, 10, 15, and 20, and then likewise on the vertical axis. And so these are the sorts of figures we would print in advance, and they can be used to investigate scatter plots and residual plots and QQ plots and so forth. And effectively, any image that cannot obviously be translated into text can be translated into a tactile image. That's the expression for these. So if you remember that original table going back, we've covered all 6 boxes. We had mathematical writing with JAWS or ASCII use of 8-bit Braille. We had computer programming with the terminal window and the BrailleR package. And we have images with both this VI wrapper command and tactile images shown here. So very briefly, those are the accommodations that we used in the class. And so I wanted to end with just a few conclusions, the references, and then also to thank some folks. The book that we used is Stat2 by Cannon et al. And we're very grateful to the publisher, W.H. Freeman. They sent us a high-quality PDF version of the text, which allowed some of our graduate students to copy the text into text files, and they would then retype the equations in LaTeX, and that made the textbook accessible to our students. The paper that this talk is about is shown in the second bullet point, and I really can't thank Jonathan Godfrey enough. He's an expert, and he's very heavily involved in mathematics and statistics education for the blind. He was the author of the BrailleR package, and he maintains it. And he's written a number of very high-quality papers that I encourage everyone to look at. And finally, there's rather a lot of people at Wake Forest we should thank. We've had a number of students produce some of these materials: Spencer Ashley, Sarah Renke, Rebecca Katsanis, and Hunter Denham currently. We want to thank the Wake Forest Learning Assistance Center for their support, and again, Jonathan Godfrey of Massey University. So thank you very much for your time.
Thank you very much. We have a few questions from our audience, so let me ask those. First of all, did the student have to learn LaTeX? And if so, how was that done at the same time she was being asked to use it in class?
Yes, the student did have to learn LaTeX. She did not use it in her AP Statistics course. And we felt justified in teaching LaTeX because the student was planning to possibly minor or major in statistics. In the end, she declared a minor. So we felt that the investment was well worth the time. What we wound up doing was registering the student for 3 credits of independent study, because in advance we knew that learning LaTeX would be a lot more time and effort on her part, and we were not certain that we would be able to cover every topic of the course in exactly the same way. The way it all turned out, the student learned LaTeX, and she completed all assignments and covered all of the topics in the regular course. So it worked out quite well in the end, but there's no question a student would need to learn some of the basics of LaTeX for this approach to work.
You talked about this a bit in your paper, but you didn't really mention much of it in the talk. Can you discuss the time and the financial commitment involved in adapting this course?
Sure. I was the instructor, so I'll say a bit about the time, and then I'll let Michael Shuman say a bit about the financing behind the scenes. It takes more time. There's no getting around that. There's time preparing the materials. We were lucky to have the assistance of some graduate students who helped us prepare the text and the tactile images. The time for me as an instructor was mostly these one-on-one meetings with the student, which provided an opportunity to clean up any confusions or errors that had arisen along the way. I I didn't keep an accurate log. I mean, it was probably in the order of several hours per week, but I think it was in the realm of the legal and moral framework of providing access to higher education. And so maybe Michael can say something about the financing.
I'll say something about financing, but also with regard to timing, not so much the time, but when we knew she was coming to Wake Forest, she mentioned right from the beginning she was interested in statistics. But I actually asked her because when it was determined that Rob's course was going to be the most appropriate first course for her sequence, and then I realized that there was such a heavy visual component to the course, we made the decision to postpone her taking that course until the spring semester so that Rob and I could spend some time researching, not only among my colleagues who were coordinating accommodations for students with disabilities on other college campuses, but so that Rob could network with some of his faculty colleagues to see, have you ever done this before? So we had a semester to do a little bit of planning before we actually approached this course for the spring. As far as finances are concerned, we ended up paying all of the grad students that helped, not only the grad students in the math department that worked specifically with the LaTeX, but also some of the grad students in our office who are working on creating text in alternative format. And we also purchased the embosser that Rob alluded to earlier. Interestingly, the embossers have been around for years, and many blind students are not really as reliant on Braille versions of text anymore because so much of it is digital. And in one of the images you saw the refreshable Braille display, which this student already owned. She brought that with her to Wake Forest. But because we realized the tactile part of this course was going to be essential, we went ahead and purchased the embosser. And we shopped around a bit, but the embosser we ended up purchasing was right at about $5,000, and that included the software used to create the Braille text.
Now, you said that the student had already taken AP statistics in high school. Since that's a more widespread course than Stat 2, are there already resources for blind students available for AP statistics, and was the student able to suggest some things that had worked for her in the past?
Yes, the student was able to suggest some things, and there are more resources. Certainly the vast majority of papers dealing with providing assistance to blind students in statistics are concerned with the introductory course, and that makes sense. That's the course that most students are going to take. It's by far the most popular. The student in our case, she came with the Braille note, and so she had used, that's the refreshable Braille display. She had used that a bit in her intro course. My overall sense, though, was that the intro course, the mathematics never gets more complicated than what could simply be dictated among two people sitting across the table. I mean, I can recite the equations in the intro course in an immediately accessible way, and a student can recite her answers back in an accessible way. Software is not essential. We don't use any software in our intro course here at Wake Forest. Mathematically, taking the square root of something is about as difficult as that gets. So I think there are issues that don't quite rise to prominence in the first course because you can handle them with a close one-on-one relationship between the student and the instructor.
All right. I think that's it for our questions. I would like to remind our audience that next month, the October JSE webinar will be on identifying statistical concepts associated with high and low levels of self-efficacy to teach statistics in middle grades, and that will be given by Lee Harold Williams, and Michelle will be back to host that. Also, as you leave the webinar, you'll be given the opportunity to fill out a brief survey to give our guest speakers and cause feedback on this webinar, so I hope you'll take a few minutes to do that. I'd like to thank our speakers very much for this interesting presentation and also how much hard work you put into developing these resources. I'm sure that a lot of us will end up needing to look back at this later as we meet new students with special needs. So thanks to all of you. Thanks for the good discussion, and we hope to see you soon.